What if everything you thought you knew about the universe's expansion was just the tip of the cosmic iceberg? Here's a fact that might make your brain ache. The universe isn't just expanding, it's doing so faster than the speed of light. That's right, galaxies are racing away from us at speeds that defy the very laws of physics as we understand them. But why? What force, what hidden mechanism could possibly drive such an unimaginable phenomenon? And why does it challenge everything science has tried to explain? This isn't just a question for astrophysicists or philosophers, it's a puzzle that reshapes how we see our place in the cosmos. The expansion of the universe isn't just some abstract concept, it's the story of existence itself. And today, we're diving into 15 mind-bending theories that attempt to explain this cosmic mystery. From mysterious dark energy to the possibility of parallel universes, these ideas don't just challenge science, they force us to rethink the very fabric of reality. So, what if the universe's expansion isn't what we think it is? What if it's driven by forces we can't even detect yet? Or what if it's a sign that our understanding of space, time, and energy is fundamentally incomplete? These are the questions we'll explore as we unravel 15 groundbreaking theories that push the boundaries of what we know. Get ready, because by the end of this journey, the universe might look a little less familiar and a whole lot more mysterious. The story of our universe begins with the Big Bang, an explosion of energy and matter that set everything into motion. Think of it like the ultimate starting gun, firing off the creation of space, time, and all the matter we know today. But here's where it gets fascinating. The universe didn't just stop expanding after that initial burst. Instead, it kept growing, stretching out like an endless cosmic canvas. This idea of an expanding universe wasn't always widely accepted. In fact, it took a groundbreaking discovery by astronomer Edwin Hubble to change the way we see the cosmos. In the 1920s, Hubble observed that distant galaxies were moving away from us, and the farther away they were, the faster they seemed to be receding. How did he know? By studying something called redshift, a phenomenon where the light from these galaxies shifts toward the red end of the spectrum as they move away. It's a bit like listening to a siren on a speeding ambulance. As it moves farther from you, the sound drops in pitch. In the same way, the light from galaxies stretches out, revealing their movement. Hubble's discovery was a game changer. It confirmed that the universe wasn't static but was instead expanding, with galaxies drifting apart like dots on an inflating balloon. But here's where things get even more mysterious. As scientists studied this expansion further, they found that it wasn't just continuing, it was speeding up. And that's where dark energy comes in. Dark energy is the name we've given to the mysterious force driving this accelerated expansion. It's like an invisible hand pushing the universe apart faster and faster, even though we can't see it or fully understand it. Imagine blowing up a balloon, but instead of slowing down as it gets bigger, it starts inflating faster and faster on its own. That's the kind of puzzling behavior we're dealing with when it comes to dark energy. What makes this even more intriguing is that dark energy challenges some of the most fundamental principles of physics. It doesn't fit neatly into our current understanding of how the universe works, and that's what makes it such a hot topic in science today. But before we dive into the mysteries of dark energy and the theories trying to explain it, let's take a step back and explore how this expanding universe came to be in the first place. After all, every great cosmic mystery starts with a beginning, and the Big Bang is just the opening chapter. Dark energy is one of the most mysterious and powerful forces in the universe, yet we can't see it, touch it, or even fully understand it. Making up about 68% of the cosmos, this invisible energy is the reason our universe isn't just expanding, it's doing so at an accelerating rate. Imagine blowing up a balloon, but instead of slowing down as it gets bigger, it starts inflating faster and faster. That's the effect dark energy has on the fabric of space itself. But what exactly is it? The leading explanation for dark energy comes from something Albert Einstein once called his greatest blunder, the cosmological constant. Originally, Einstein introduced this concept to balance his equations and describe a static universe, one that didn't expand or contract. When the universe's expansion was later discovered, he dismissed the idea. But now, the cosmological constant is back in the spotlight, helping us explain why galaxies are racing away from each other faster than ever. It suggests that dark energy might be an intrinsic property of space itself, a kind of energy woven into the very fabric of the cosmos, pushing everything apart. Saul Perlmutter, a Nobel Prize-winning physicist, once described dark energy as the most profound mystery in all of science. His groundbreaking work in the late 1990s revealed that the universe's expansion isn't slowing down as many had expected, but speeding up. This discovery turned cosmology upside down, forcing us to rethink everything we thought we knew about gravity, energy, and the fate of the universe. But even with all we've learned, dark energy remains elusive. Could it be a property of space itself, as the cosmological constant suggests? Or is it something even stranger, something we haven't even imagined yet? While dark energy is the most widely accepted explanation for the universe's accelerating expansion, it's not the only possibility. Some scientists argue that our understanding of gravity might be incomplete, or that there could be other forces at play that we haven't yet detected. These alternative theories challenge the very foundation of modern physics, suggesting that dark energy might not be the final answer. As we continue to explore the cosmos, one thing is clear: the universe still holds countless secrets, and dark energy is just the beginning of the story. So, what if there's more to cosmic expansion than meets the eye? What other forces could be shaping the fate of the universe? Imagine a pot of water on the stove beginning to boil. Tiny bubbles form, rise, and pop, each one a fleeting, self-contained world. Now picture this on a cosmic scale. What if our universe is just one of countless bubbles, each floating in an infinite cosmic soup? This is the essence of the multiverse theory, a mind-bending idea that suggests our universe might not be alone. Instead, it could be one of many, each with its own unique set of physical laws and constants. Some might have gravity so weak that stars never form, while others might collapse in on themselves almost instantly. And here's the kicker: these bubble universes could be expanding independently, like balloons inflating in an endless void, completely unaware of one another's existence. This theory doesn't just challenge our understanding of the universe, it shatters the very notion of a single, expanding cosmos. Instead of one grand story of cosmic expansion, the multiverse theory paints a picture of countless narratives unfolding simultaneously, each with its own rules and destiny. It's a concept that stretches the limits of our imagination, forcing us to reconsider what it means to exist in the vastness of reality. But how does this tie into the expansion of our own universe? If the multiverse is real, then the expansion we observe might not be the whole story. Instead of a single, uniform expansion, we could be witnessing the growth of just one bubble in an infinite sea of possibilities. It's like watching a single ripple on the surface of an ocean, unaware of the countless waves crashing elsewhere. And speaking of waves, this leads us to the next fascinating theory: quantum mechanics. Could the strange, unpredictable behavior of particles at the smallest scales hold the key to understanding the expansion of the universe? Let's dive into that next. But what if the universe's expansion isn't just about galaxies moving apart? What if the very fabric of space itself is being stretched by something far more mysterious? To explore this, we need to step into the quantum realm, a place where the rules of everyday physics no longer apply. Here, particles and antiparticles pop in and out of existence in a cosmic dance that defies intuition. These fleeting appearances, known as quantum fluctuations, might hold the key to understanding why our universe is expanding. Imagine space as a vast, bubbling ocean. Even in the emptiest regions where it seems like nothing exists, tiny ripples of energy constantly emerge and vanish. This is the quantum vacuum, a seething sea of potential where particles briefly come to life before disappearing back into nothingness. But here's the fascinating part. These fluctuations aren't just random noise. According to quantum theory, they generate energy, what physicists call vacuum energy. And this energy, though incredibly small on a local scale, might have a profound cumulative effect on the cosmos as a whole. Leonard Susskind, a leading figure in theoretical physics, has described this vacuum energy as a kind of cosmic fuel. It's possible that this energy is pushing space itself apart, acting as a hidden force behind the universe's accelerating expansion. But there's a catch. When physicists try to calculate how much energy these quantum fluctuations should produce, the numbers they get are staggeringly large, far larger than what we observe in the real universe. This mismatch, known as the cosmological constant problem, remains one of the biggest unsolved puzzles in physics. So, could quantum fluctuations and vacuum energy truly be driving the universe's expansion? The answer isn't clear yet, but the idea is compelling. It suggests that the tiniest, most fleeting phenomena in the quantum world might have a monumental impact on the cosmos at large. And as we continue to unravel these mysteries, we're reminded just how interconnected the scales of existence truly are, from the infinitesimal to the infinite. Now, while quantum mechanics offers one intriguing perspective, there's another force at play in the cosmic expansion debate: gravity. It's a force we're all familiar with, but in the context of the universe's expansion, it takes on a whole new dimension. Could gravity be working in ways we haven't fully understood? Let's explore that next. What if gravity doesn't work the way we've always thought? For decades, Einstein's theory of general relativity has been the cornerstone of our understanding of gravity, shaping everything from black holes to the expansion of the universe. But what if there's more to the story? Enter modified gravity theories, a bold set of ideas that challenge Einstein's framework by proposing that gravity behaves differently on cosmic scales. One of the most well-known alternatives is MUND, or modified Newtonian dynamics. Instead of relying on dark energy to explain the universe's accelerating expansion, MUND suggests that our understanding of gravity might simply be incomplete. At the heart of MUND is the idea that gravity doesn't weaken as quickly over vast distances as Newton or Einstein predicted. Instead, it behaves slightly differently in regions where gravity is extremely weak, like the outer edges of galaxies. This tweak to the rules of gravity could explain why galaxies rotate faster than expected without needing to invoke invisible dark matter or mysterious dark energy. It's a radical idea, but one that has sparked serious debate among scientists. If MUND or similar theories are correct, it could mean that dark energy isn't driving the universe's expansion. Gravity itself might be the key. But these theories aren't without their challenges. Modified gravity models struggle to explain certain phenomena, like the behavior of galaxy clusters or the precise measurements of the cosmic microwave background. And while MUND offers an intriguing alternative, it hasn't yet been able to fully replace the elegant framework of general relativity. Still, the implications are profound. If gravity works differently than we've assumed, it could reshape our understanding of everything from the birth of the universe to its ultimate fate. This brings us to another fascinating possibility. What if the very fabric of spacetime holds the answers? The next theory we'll explore takes us even deeper into the mysteries of the cosmos, suggesting that the expansion of the universe might be tied to the nature of spacetime itself. Now let's stretch our minds a bit literally. Imagine the universe as a rubber sheet, smooth and flexible. What happens when you pull on that sheet? It stretches, right? This is a lot like what scientists believe is happening with spacetime itself. The very fabric of the universe isn't static, it's dynamic, expanding as if being pulled in all directions. This idea, known as spacetime stretching, is one of the most fascinating ways to think about why the universe is growing larger. Think of it this way: galaxies aren't just drifting apart through empty space. Instead, the space between them is actually stretching, like the rubber sheet being tugged. This means that even if galaxies aren't moving much on their own, the expansion of spacetime carries them away from each other. It's why we observe distant galaxies receding from us faster than closer ones. The farther they are, the more spacetime there is to stretch. And this isn't just a thought experiment. It's supported by decades of observations, including the famous redshift of light from distant galaxies, which shows they're moving away from us. But here's where it gets even more intriguing. This stretching of spacetime isn't just happening randomly, it's tied to something much deeper, the very nature of the universe itself. And that leads us to the next big question: what could have set this expansion in motion in the first place? To answer that, we need to look back, way back, to the very beginning of the cosmos. Because the key to understanding why spacetime stretches might lie in the explosive events that shaped the early universe. So, what if I told you that the universe didn't just expand after the Big Bang, it exploded into existence faster than the speed of light? This isn't science fiction, it's cosmic inflation, one of the most groundbreaking ideas in modern cosmology. Proposed by physicist Alan Guth in the 1980s, inflation theory suggests that in the tiniest fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing from something smaller than an atom to something trillions of times its size. Guth described it as the ultimate free lunch, where space itself stretched faster than light could keep up. But why does this matter? Well, inflation solves two of the biggest puzzles in cosmology: the horizon problem and the flatness problem. The horizon problem asks why the universe looks so uniform. If you look in opposite directions, the cosmic microwave background, the afterglow of the Big Bang, appears almost identical in temperature. But without inflation, these regions would never have had time to interact or balance out. Inflation solves this by proposing that the universe was once small enough to reach thermal equilibrium before rapidly expanding. As for the flatness problem, inflation explains why the universe appears flat, like a perfectly stretched sheet, rather than curved. This rapid expansion smoothed out any wrinkles, leaving us with the universe we see today. Alan Guth once said, "Inflation is a mechanism that turns a tiny, smooth speck of space-time into the vast, uniform cosmos we inhabit." It's a bold idea, but one that has held up remarkably well under scrutiny. Yet, as elegant as inflation is, it raises new questions. What powered this rapid expansion? And what role do mysterious, exotic particles play in shaping the universe? That's where our journey takes us next, into the realm of particles so strange, they might just hold the key to understanding everything. One of the most intriguing possibilities in the search for answers about the universe's expansion lies in the realm of exotic particles, entities we can't yet detect but might hold the key to understanding the cosmos. These particles, invisible to our current technology, could be silently shaping the fabric of space and time. Among them, dark matter stands out as a prime candidate. Even though it doesn't interact with light, its gravitational effects are undeniable. Galaxies spin faster than they should, and clusters of galaxies bend light in ways that can't be explained by visible matter alone. Dark matter, though mysterious, seems to be weaving an invisible web that holds the universe together. But what if it's also playing a role in pushing it apart? Scientists have proposed a variety of exotic particles that could be hiding in the shadows of the cosmos. Take actions, for example, hypothetical particles so light and elusive that they barely interact with ordinary matter. If they exist, they might have been created in vast numbers during the early universe, and their presence could subtly alter the way space behaves over time. Then there are sterile neutrinos, a speculative cousin of the neutrinos we know. Unlike regular neutrinos, which barely interact with matter, sterile neutrinos might not interact at all, making them perfect candidates for dark matter. These particles, if they're out there, could be contributing to the universe's expansion in ways we're only beginning to imagine. But here's the thing, while these ideas are fascinating, they're still just that, ideas. We haven't directly detected actions, sterile neutrinos, or any other exotic particles yet. The hunt is on, though. Experiments deep underground, in particle colliders, and even in space are searching for clues. Every discovery, or even every dead end, brings us closer to understanding whether these invisible entities are truly shaping the cosmos. As we ponder these possibilities, it's worth considering how the universe's geometry might also play a role in its expansion. Could the shape of space itself hold the answers? That's where our journey takes us next, as we explore how the curvature of the cosmos might be influencing everything we see and don't see. Now let's shift our focus to the shape of the universe itself, a question that might sound abstract at first but has profound implications for how everything expands. Is the universe flat, open, or closed? Believe it or not, the geometry of the cosmos isn't just a theoretical curiosity. It's a key piece of the puzzle in understanding why the universe grows the way it does. Picture a flat sheet of paper. This is the simplest way to visualize a flat universe. In this scenario, parallel lines stay parallel forever, and the rules of geometry we learned in school hold true on the grandest scale. But what if the universe isn't flat? Imagine stretching that sheet of paper into a saddle shape, an open universe where parallel lines eventually diverge. Or think of it as wrapping the paper into a sphere, a closed universe where parallel lines eventually meet. These shapes aren't just artistic metaphors, they're mathematical descriptions of how space itself curves. So, why does this matter? If the universe is flat, as current observations suggest, it tells us something extraordinary about the balance of energy and matter. A flat universe implies that the total energy density is just right. Not too much, not too little, to keep space from curving. This delicate balance is one of the strongest hints we have that dark energy exists, driving the acceleration of cosmic expansion. But if the universe were closed like a sphere, it would eventually stop expanding and collapse back in on itself. And if it were open like a saddle, it would stretch forever, growing colder and emptier with time. The fact that our universe appears flat suggests that dark energy isn't just a placeholder in our equations, it's a real force shaping the fate of everything. And here's where things get even more intriguing. The shape of the universe doesn't just affect how it expands, it also ties into the arrow of time. If the universe is flat and expanding, it raises questions about why time moves forward and not backward. This leads us to the next fascinating theory, which connects cosmic expansion to the very nature of time itself. How does the universe's growth influence the direction of time? And could this help explain why the past, present, and future feel so distinct? Let's explore this next layer of the mystery. One of the most fascinating aspects of the universe's expansion is its relationship with time and entropy. Think about it. Why does time always seem to move forward? Why do things break down, mix together, and become more disordered over time? This is entropy at work, a fundamental principle of thermodynamics that describes how systems naturally move toward chaos. But here's the kicker. Entropy isn't just about your coffee cooling down or your room getting messy. It might also hold the key to understanding why the universe is expanding. At the heart of this idea is the arrow of time, the one-way direction in which time flows. We experience time as moving forward, never backward, and entropy is closely linked to this. As entropy increases, so does the complexity of the universe. Some scientists suggest that the expansion of the universe and the increase of entropy are two sides of the same cosmic coin. As the universe grows, it creates more space for entropy to rise, and this relentless march toward disorder might actually be driving the expansion itself. It's almost as if time, in its forward motion, is pushing the universe to stretch and grow. But could this mean that time itself is a force behind the expansion? It's a mind-bending question. If entropy is increasing as the universe expands, could the very nature of time be propelling this cosmic growth? Some theories propose that the arrow of time and the expansion of space are deeply intertwined, with each influencing the other in ways we're only beginning to understand. It's a reminder that the universe isn't just a collection of objects in space. It's a dynamic, evolving system where time, energy, and matter are all connected. As we peel back these layers, another intriguing question arises. What role do black holes play in this cosmic dance? These mysterious objects, with their immense gravitational pull, might hold secrets about how the universe expands and how time and entropy interact on the grandest scales. But that's a story for the next part of our exploration. For now, let's sit with this thought. The universe isn't just expanding, it's unfolding in time, driven by forces we're only starting to comprehend. And every moment brings us closer to unraveling the mystery. Black holes have long been one of the most mysterious and fascinating objects in the universe. But what if these cosmic giants aren't just lurking in space? What if they're actively shaping the fabric of the cosmos itself? Some scientists have proposed a startling idea. Black holes might be contributing to the universe's expansion. It's a theory that ties together some of the most mind-bending concepts in physics, from Hawking radiation to the information paradox. Stephen Hawking, one of the most influential physicists of our time, first proposed that black holes aren't entirely black. Instead, they emit tiny amounts of radiation, now known as Hawking radiation. Over time, this radiation causes black holes to lose mass and eventually evaporate. But here's where it gets even more intriguing. As black holes evaporate, they release energy back into the universe. Some researchers suggest that this energy could be acting as a kind of cosmic fuel, subtly pushing the universe to expand faster. It's a wild idea, but it's rooted in the math of quantum mechanics and general relativity. Then there's the information paradox, a puzzle that's been haunting physicists for decades. When matter falls into a black hole, what happens to all the information it contains? According to quantum mechanics, information can't be destroyed. It has to be preserved somehow. Hawking's work hinted that this information might escape as Hawking radiation, but the details are still far from clear. If black holes are somehow encoding and releasing information back into the universe, could this process also be influencing the rate of cosmic expansion? The connections are speculative, but they open up a whole new way of thinking about the role black holes play in the grand scheme of things. And as we ponder the mysteries of black holes, another theory looms on the horizon, one that challenges our very understanding of reality. Could the universe itself be a hologram? This idea, known as the holographic principle, suggests that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface. It's a concept that could redefine how we see space, time, and even black holes themselves. What if everything we see, touch, and experience in this vast universe is nothing more than a projection, a cosmic illusion? This is the mind-bending idea at the heart of the holographic principle. Imagine the universe as a giant hologram where all the information about everything within it, stars, galaxies, even you and me, is encoded on a two-dimensional surface at its boundary. It's like watching a 3D movie where the images seem to pop out, but in reality, they're all being projected from a flat screen. In this theory, our three-dimensional reality might just be a shadow of the true, higher-dimensional information stored on the universe's outer edge. This idea turns our understanding of cosmic expansion on its head. Instead of the universe growing uniformly in all directions like an inflating balloon, the holographic principle suggests that the expansion we observe could be a side effect of how this information is processed and projected. It's as if the universe is running a cosmic simulation, and the expansion we measure is just part of the code. This challenges the traditional view that space itself is stretching, offering a radical alternative that ties the fabric of reality to information itself. But how does this connect to the bigger picture? The holographic principle doesn't just redefine expansion. It hints at a deeper connection between the very small and the very large. It suggests that the quantum realm, the world of particles and forces, might be intimately linked to the structure of the cosmos as a whole. This idea leads us to another fascinating concept, one that blurs the lines between particles and space itself: quantum entanglement. And that's where our journey takes us next. Quantum entanglement is one of the most baffling phenomena in physics, and it might hold a key to understanding the universe's expansion. At its core, entanglement is a strange connection between particles, where the state of one instantly influences the state of another, no matter how far apart they are. Einstein famously called it spooky action at a distance, but today scientists are asking, could this spooky connection play a role in the way the universe grows? Some researchers, like quantum physicist Juan Maldacena, suggest that entangled particles might form a vast, invisible network across the cosmos. This network, they propose, could be generating forces that push space itself to stretch faster and faster. It's a radical idea, but it's grounded in the mathematics of quantum mechanics and general relativity, two pillars of modern physics. If true, it would mean that the tiniest particles in existence are somehow shaping the fate of the entire universe. But how exactly could this work? Imagine the universe as a cosmic web, with entangled particles acting like threads that pull and push space-time in ways we're only beginning to understand. This theory challenges us to rethink not just our understanding of expansion, but also the very fabric of reality. And as we explore this idea, it leads us to another intriguing possibility. What if the universe isn't just expanding, but cycling through phases of growth and contraction? That's where the concept of a cyclic universe comes into play. One of the most mind-bending ideas in cosmology is the cyclic universe theory, which suggests our universe isn't a one-time event but part of an endless loop of expansion and contraction. Picture the cosmos as a cosmic heartbeat pulsing rhythmically over eons. Instead of a single Big Bang marking the beginning of everything, this theory proposes that the universe breathes, expanding for billions of years before collapsing back in on itself, only to explode outward again in a new cycle. It's like a cosmic reset button pressing itself over and over. This idea challenges the traditional view of the Big Bang as a singular, one-and-done event. If the cyclic universe theory holds, our universe isn't unique. It's just one in an infinite series of universes, each born from the collapse of the previous one. Some physicists suggest that dark energy, the mysterious force driving the universe's accelerated expansion, could play a key role in this process. As the universe expands, dark energy might eventually weaken, allowing gravity to take over and pull everything back together in what's called the Big Crunch. Then the cycle begins anew, but how could such a process even work? One possibility lies in the behavior of space-time itself. As the universe contracts, it might reach a point where the laws of physics as we know them break down, allowing for a fresh start. It's a bit like crumpling up a piece of paper and then smoothing it out again. What was once a chaotic mess becomes a clean slate, ready for a new story. This theory isn't without its challenges, though. Critics argue that the cyclic model struggles to explain the observed uniformity of the cosmic microwave background, the faint glow left over from the early universe. But for its supporters, the cyclic universe offers a poetic alternative to the idea of a one-time beginning, suggesting instead that the cosmos is eternal, endlessly cycling through phases of birth, death, and rebirth. And speaking of cosmic rhythms, this idea of cycles and patterns leads us to another fascinating possibility. What if the universe's expansion isn't just happening in the three dimensions we're familiar with? What if higher dimensions are at play, shaping the very fabric of reality? That's where our next theory takes us. What if everything we see, the stars, galaxies, and even the vast emptiness of space, is just a tiny slice of a much larger reality? One of the most mind-bending theories to explain the universe's expansion is the idea that our entire cosmos exists within higher dimensions. This isn't science fiction. It's a serious scientific proposal that could reshape how we understand the very fabric of existence. To grasp this, let's take a step back and think about dimensions in a simpler way. Imagine a flat, two-dimensional creature living on a piece of paper. To this creature, the world is entirely flat. Up, down, left, and right are all it knows. But what happens if you, as a three-dimensional being, lift that piece of paper into the air? The 2D creature wouldn't even comprehend the concept of up in the way you do. It would just notice that its world is changing, expanding in ways it can't fully explain. In the same way, our three-dimensional universe might be embedded in a higher dimensional space. Theories like string theory and brain-world cosmology suggest that these extra dimensions could be the key to understanding cosmic expansion. String theory, for instance, proposes that the fundamental building blocks of the universe are tiny, vibrating strings, and these strings exist in up to 10 or 11 dimensions. Meanwhile, brain-world cosmology imagines our universe as a brain, a sort of membrane floating within a higher dimensional space. Just as the 2D creature couldn't see the third dimension, we might be oblivious to these extra dimensions, even as they influence the behavior of our universe. But how does this connect to expansion? Think of it like this. If our universe is a brain in a higher dimensional space, the energy from those extra dimensions could be pushing or pulling on our brain, causing it to stretch. This stretching could manifest as the expansion we observe in the cosmos. It's a bit like blowing up a balloon, except the balloon exists in a space we can't see or directly measure. While this might sound like wild speculation, it's grounded in mathematical models that scientists are actively exploring. And it opens up a whole new way of thinking about the universe, one where the answers to our biggest questions might lie just beyond the limits of our perception. Now, as we edge closer to the end of our journey through these 15 theories, there's one final idea that takes this concept of hidden dimensions to an even more extraordinary level. What if the universe isn't just shaped by higher dimensions, but is something else entirely? Something that might make us question the very nature of reality itself. What if everything we see, everything we experience, and even the very fabric of the universe itself is nothing more than lines of code in a cosmic simulation? This is the bold and mind-bending premise of the simulation hypothesis, a theory that suggests our reality might be an artificial construct designed by an advanced civilization. Proponents of this idea argue that the universe's expansion could simply be a programmed feature, deliberately coded into the simulation to mimic the behavior of a real cosmos. But if that's true, what does that say about the nature of reality? Could the universe's expansion be a glitch in the code, or perhaps an intentional mechanism designed to keep the simulation running smoothly? The simulation hypothesis doesn't just challenge our understanding of the universe, it flips it entirely on its head. If we're living in a simulation, then the laws of physics, the constants of nature, and even the passage of time might not be fundamental truths, but rather parameters set by the creators of this virtual reality. Think of it like this: in a video game, the rules of the world are defined by the game's code. Gravity, speed, and even the flow of time are all programmed features. Now scale that up to the universe. Could the accelerating expansion of space be part of some grand design, a feature built into the system to keep the simulation dynamic and evolving? But here's the kicker: if this theory holds any weight, it raises profound questions about our place in the cosmos. Are we merely characters in someone else's simulation, or is there something more to our existence? Some scientists argue that if the simulation hypothesis is true, we might never be able to prove it. After all, how could we detect the edges of a simulated universe if the entire framework is designed to feel seamless and infinite? Others suggest that glitches or anomalies in the laws of physics, might be our only clues, tiny cracks in the code that reveal the artificial nature of our reality. As we've explored these 15 theories about the universe's expansion, it's clear that each one challenges our understanding in unique and fascinating ways. From dark energy to quantum fluctuations, and now the simulation hypothesis, the mystery of why the universe expands continues to push the boundaries of science and imagination. These theories don't just seek to explain the cosmos, they invite us to rethink what we know about existence itself. And as we prepare to wrap up this journey, let's take a moment to reflect on how far our curiosity has taken us and how much further it might yet go. As we reach the end of our exploration into the universe's expansion, let's take a moment to reflect on the 15 remarkable theories we've uncovered. Each one challenges the very foundation of our scientific understanding in profound and unexpected ways. From the mysterious dark energy driving galaxies apart to the mind-bending implications of multiverses, these ideas remind us that the cosmos is far more enigmatic than we often assume. They push the boundaries of what we think we know, inviting us to question, to wonder, and to dream bigger. Think about it, something as simple as the Big Bang, the event that started it all, leads us to questions we still can't fully answer. Why did it happen? What came before? And then there's dark matter, an invisible force that shapes the universe yet remains just out of our grasp. Theories like cosmic inflation suggest our universe might be just one bubble in a vast cosmic foam, while others hint at the possibility of higher dimensions we can't even perceive. Each of these ideas doesn't just challenge science, it challenges us to rethink our place in the grand scheme of things. What's truly humbling is how much we still don't know. The universe isn't just expanding, it's expanding our minds, forcing us to confront the limits of human knowledge. As Carl Sagan once said, somewhere, something incredible is waiting to be known. And it's this sense of wonder, this relentless curiosity that drives us forward. The universe's expansion isn't just a scientific puzzle, it's a reminder that the journey of discovery is never ending. So, what do you think? Which of these theories resonated with you the most? Do you believe the answers lie within our reach, or are we destined to keep chasing the unknown? Let's continue the conversation in the comments below. Share your thoughts, your questions, and your favorite theories. And if you've enjoyed this journey through the cosmos, don't forget to subscribe for more mind-expanding content. Together, let's keep exploring the mysteries of the universe, because as Neil deGrasse Tyson beautifully put it, the universe is under no obligation to make sense to you. And maybe, just maybe, that's what makes it so extraordinary. Remember, the universe's expansion isn't just a scientific question, it's a journey into the unknown. And what a journey it is!